Okay, good. I'm recording. Welcome. So this is part 12. Yeah, part 12. So yeah, last thing I did, the first quiz of this section, and gonna finish all this today. Yeah, it's just shit. It's a lot of videos. Holy crap. Okay. Anyway, let's just start. Order of operations. Okay, let's go. Spam this thing, right?
In this video, we're going to talk a little bit about order of operations. And
But am I recording? Yes, I am.
want you to pay close attention because really everything else that you're going to do in this video, we're going to talk a little bit about order of operations. And I want you to pay close attention because really everything else that you're going to do in mathematics is going to be based on you having a solid grounding in order of operations.
Yeah,
so what do we even mean when we say order of operations? So let me give you an example. The whole point is so that we have one way to interpret a mathematical statement. So let's say I have the mathematical statement 7 plus 3 times 5. Now, if we didn't all agree on order of operations, there would be two ways of interpreting this statement. You could just read it left to right. So you could say, well, let me just take 7 plus 3. You could say 7 plus 3, and then multiply that times 5. And 7 plus 3 is 10. And then you multiply that by 5. 10 times 5, it would get you 50. So that's one way you would interpret it if we didn't agree on an order of operations. Maybe it's a natural way. You just go left to right. Another way you could interpret it, you say, oh, I like to do multiplication before I do addition. So you might interpret it as, I'll try to color code it, 7 plus, and you do the 3 times 5 first. 7 plus 3 times 5, which would be 7 plus 3 times 5 is 15.
Wait,
and 7 plus...
Yo, this is this ain't part 12. Yeah, we're certain part 11, dude. I really suck at math.
15 is 22. is 22. So notice, we interpreted the statement in two different ways. This was just straight left to right, doing the addition, then the multiplication. This way, we did the multiplication first, then the addition. We got two different answers. And that's just not cool in mathematics.
Just a sec. Okay, cool, I'm back.
If this was part of some effort to send something to the moon because two people interpreted it a different way, or one computer interpreted one way and another computer interpreted another way, the satellite might go to Mars. So this is just completely unacceptable. And that's why we have to have an agreed upon order of operations, an agreed upon way to interpret this statement. So the agreed upon order of operations is to do parentheses first. Let me write it over here. Parentheses first, then do exponents. If you don't know what exponents are, don't worry about it right now. Exponents. And in this video, we're not going to have any exponents in our examples, so you don't really have to worry about them for this video. Then you do multiplication. I'll just write mult short for multiplication. Then you do multiplication and division next. They kind of have the same level of priority. And then finally, you do addition and subtraction. Finally, you do addition and subtraction. So what is this order of operations? Let me label it. This right here, that is the agreed upon order of operations. And if we follow these order of operations, we should always get to the same answer for a given statement. So what does this tell us? What is the best way to interpret this up here? Well, we have no parentheses. Parentheses look like that. Those little curly things around numbers. We don't have any parentheses here. I'll do some examples that do have parentheses. We don't have any exponents here, but we do have some multiplication and division, or we actually just have some multiplication. So the order of operations say, do the multiplication and division first. So it says, do the multiplication first. That's a multiplication. So it says, do this operation first. It gets priority over addition or subtraction. So if we do this first, we get the 3 times 5, which is 15. And then we add the 7. The addition or subtraction, I'll do it here. Addition, we just have addition. Just like that. So we do the multiplication first, get 15, then add the 7. 22. So based upon the agreed order of operations, this right here is the correct answer, the correct way to interpret this statement. Let's do another example. I think it'll make things a little bit more clear. And I'll do the example in pink. So let's say I have 7 plus 3, 7 plus 3, put some parentheses there, times 4 divided by 2 minus 5 times 6. So there's all sorts of crazy things here. But if you just follow the order of operations, you'll simplify it in a very, I guess, clean way. And hopefully we'll all get the same answer. So let's just follow the order of operations. The first thing we have to do is look for parentheses. Are there parentheses here? Yes, there are. There's parentheses around the 7 plus 3. So it says, let's do that first. So 7 plus 3 is 10. So this we can simplify, just looking at this order of operations, to 10 times all of that. Let me copy and paste that so I don't have to keep rewriting it. So let me copy and let me paste it. So that simplifies to 10 times all of that. We did our parentheses first. Then what do? There are no more parentheses in this expression. Then we should do exponents. I don't see any exponents here. And just so if you're curious what exponents look like, an exponent would look like 7 squared. You'd see these little small numbers up in the top right. We don't have any exponents here, so we don't have to worry about it. Then it says to do multiplication and division next. So where do we see multiplication and division? We have a multiplication, a division, a multiplication again. Now, when you have multiple operations at the same level, when our order of operations, multiplication and division, are at the same level, then you do left to right. So in this situation, you're going to multiply by 4 and then divide by 2. You won't multiply by 4 divided by 2. But then we'll do the 5 times 6 before we do the subtraction right here. So let's figure out what this is. So we'll do this multiplication first. We'll do that multiplication first. We could simultaneously do this multiplication because it's not going to change things. But I'll do things one step at a time. So the next step we're going to do is this 10 times 4. 10 times 4 is 40. 10 times 4 is 40. Then you have 40 divided by 2. Let me copy and paste all of that again. Then it simplifies to that right there. Remember, multiplication and division, they're at the exact same level, so we're going to do it left to right. You could also express this as multiplying by 1/2, and then it wouldn't matter the order. But for simplicity, multiplication and division go left to right. So then you have 40 divided by 2 minus 5 times 6. So division, you just have one division here. You want to do that. This is going to take, you have this division, then you have this multiplication. They're not together, so you can actually kind of do them simultaneously. And to make it clear that you do this before you do the subtraction, because multiplication, division take priority over addition, subtraction, we could put parentheses around them to say, look, we're going to do that and that first before I do that subtraction, because multiplication, division have priority. So 40 divided by 2 is 20. We're going to have that minus sign. Minus 5 times 6 is 30. 20 minus 30 is equal to negative 10. And that is the correct interpretation of that. So I want to make something very, very, very clear. If you have things at the same level, so if you have 1 plus 2 minus 3 plus 4 minus 1. So addition and subtraction are all at the same level in order of operations. You should go left to right. So this, you should interpret this as 1 plus 2 is 3. 3, so this is the same thing as 3 minus 3 plus 4 minus 1. Then you do 3 minus 3 is 0 plus 4 minus 1. Or this is the same thing as 4 minus 1, which is the same thing as 3. You just go left to right. Same thing if you have multiplication and division. All on they're at the same level. So if you have 4 times 2 divided by 3 times 2, you do 4 times 2 is 8 divided by 3 times 2. And you say 8 divided by 3 is, well, we'll get a fraction there. It would be 8/3. So this would be 8/3 times 2. And then 8/3 times 2 is equal to 16/3. over 3. That's how you interpret it. You don't do this multiplication first and divide the 2 by that and all of that. Now, the one time where you can be loosey-goosey with order of operations, if you have all addition or all multiplication. So if you have 1 plus 5 plus 7 plus 3 plus 2, does not matter what order you do it in. You can do the 2 plus 3. You could go from the right to the left. You could go from the left to the right. You could start someplace in between. If it's only all addition. And the same thing is true if you have all multiplication. If it's 1 times 5 times 7 times 3 times 2, does not matter what order you're doing it. That's only when it's all multiplication or all addition. If there's some division in here, if there's some subtraction in here, you're best off just going left to right.
Well, okay. Ended abruptly.
We're asked to simplify 8 plus 5 times 4 minus, and then in parentheses, 6 plus 10 divided by 2 plus 44. Whenever you see some type of...
I'm going to get pen and paper. Got him. It's running. It's not paused. Yeah, cool. Cool.
Crazy expression like this where you have parentheses and addition and subtraction and division, you always want to keep the order of operations in mind. And let me write them down over here. So when you're doing order of operations, or really when you're evaluating any expression, you should have this in the top of your, or in kind of the front of your brain, is that the top priority goes to parentheses. Parentheses. And those are these little brackets over here, or however you want to call them. Those are the parentheses right there. That gets top priority. Then after that, you want to worry about exponents. There are no exponents in this expression, but I'll just write it down just for future reference. Exponents. One way I like to think about it is parentheses, that always takes top priority. But then after that, we go in descending order, or I guess we should say in descending order of how kind of fast that computation is. And when I say fast, how fast it grows. When I take something to an exponent, when I'm taking something to a power, it grows really fast. Then it grows a little bit slower, or shrinks a little bit slower if I multiply or divide. So that comes next. Multiply or divide. Multiplication and division comes next. And then last of all comes addition and subtraction. So these are kind of the slowest operations. This is a little bit faster. This is the fastest operation. And then the parentheses, just no matter what, always take priority. So let's apply it over here. Let me rewrite this whole expression. So it's 8
I got 61.
Plus
I hope it's correct.
5 times 4 minus, in parentheses, 6 plus 10 divided by 2 plus 44. So we're going to want to do the parentheses first. We have parentheses there and there. Now this parentheses is pretty straightforward. Well, inside the parentheses, it's already evaluated. So we could really just view this as 5 times 4. So let's just evaluate that right from the get-go. So this is going to result in 8 plus, and really when you're evaluating the parentheses, if you evaluate this parentheses, you literally just get 5. And then you evaluate that parentheses, you literally just get 4, and then they're next to each other, so you multiply them. So 5 times 4
multiply them.
is
Why
20
did you explain why?
Minus,
that's going to be a
let me stay
multiplication.
consistent with the colors, minus, and let me write the next parenthesis right there. And then inside of it, we'd evaluate this first. So let me close the parenthesis right there. And then we have plus 44. Plus 44. So what does this thing right here evaluate to, this thing inside the parentheses? Well, you might be tempted to say, well, let me just go left to right. 6 plus 10 is 16, and then divide by 2, and you would get 8. But remember, order of operations. Division takes priority over addition. So you actually want to do the division first. And we could actually write it here like this. You could imagine putting some more parentheses. Let me do it in that same purple. You could imagine putting some more parentheses right here to really emphasize the fact that you're going to do the division first. So 10 divided by 2 is 5. So this will result in 6 plus 10 divided by 2 is 5. 6 plus 5. Well, we still have to evaluate this parentheses. So this results with 6 plus 5. Well, that's 11.
That's going to be 11.
So we're left with 20. Let me write it all down again. We're left with 8
all in
plus 20 minus 6 plus 5, which is 11, plus 44.
Left or right.
And now that we have everything at this level of operations, we can just go left to right. So 8 plus 20 is 28. So you could view this as 28 minus 11 plus 44. 28 minus 11, 28 minus 10 would be 18. So this is going to be 17. It's going to be 17 plus 44. And then 17 plus 44, I'll scroll down a little bit. 17 plus 44, 7 plus 44 would be 51. So this is going to be 61. So this is going to be equal to 61. And we're done.
Okay, cool. Yeah, the same answer.
Now that we've got the basics of order of operations out of the way, let's try to tackle a really hairy and beastly problem. So here we have all sorts of parentheses and numbers flying around. But in any of these order of operations problems, you really just have to take a deep breath. And remember, we're going to do parentheses first. Parentheses, P for parentheses, then exponents. Don't worry if you don't know what exponents are, because this has no exponents in them. Then you're going to do multiplication and division. They're at the same level. Then you do addition and subtraction. So some people remember PEMDAS. But if you remember PEMDAS, remember multiplication, division, same level. Addition and subtraction, also at the same level. So let's figure what order of operations say that this should evaluate to. So the first thing we're going to do is our parentheses. And we have a lot of parentheses here. We have this expression in parentheses right there. And then even within that, we have these parentheses. So our order of operations say, look, do your parentheses first. But in order to evaluate this outer parentheses, this orange thing, we're going to have to evaluate this thing in yellow right there. So let's evaluate this whole thing. So how can we simplify it? Well, if we look at just inside of it, the first thing we want to do is simplify the parentheses inside the parentheses. So you see this 5 minus 2 right there. We're going to do that first no matter what. And that's easy to evaluate. 5 minus 2 is 3. And so this simplifies to, I'll do it step by step. Once you get the hang of it, you can do multiple steps at once. So this is going to be 7 plus 3 times the 5 minus 2, which is 3. And then you have, and all of those have parentheses around it. And of course, you have all this stuff on either side, the divide for.
Yo, I got 91. Holy
no, whoops.
Shit.
That's not what I want. I wanted to copy and paste. I want to copy and paste that right there. So copy, and then, no, that's giving me the wrong thing. It would have been easier. Let me just rewrite it. That's the easiest thing. I'm having technical difficulties. So divided by 4 times 2. And on this side, you had that 7 times 2 plus this thing in orange parentheses there. Now, at any step, you just look again. We always want to do parentheses first. We keep wanting to do this until there's really no parentheses left. So we have to evaluate this parentheses in orange here. So we have to evaluate this thing first. But in order to evaluate this thing, we have to look inside of it. And when you look inside of it, you have 7 plus 3 times 3. So if you just had 7 plus 3 times 3, how would you evaluate it? Well, look back to your order of operations. We're inside the parentheses here. So inside of it, there are no longer any parentheses. So the next thing we should do is, there are no exponents. There is multiplication. So we do that before we do any addition or subtraction. So we want to do the 3 times 3 before we add the 7. So this is going to be 7 plus,
added the 7.
And the 3 times 3 we want to do first. We want to do the multiplication first. 7 plus 9. That's going to be in the orange parentheses. And then you have the 7 times 2 plus that on the left-hand side. You have the divided by 4 times 2 on the right-hand side. And now the thing in parentheses, because we still want to do the parentheses first, pretty easy to evaluate. What's 7 plus 9? 7 plus 9 is 16. And so everything we have simplifies to 7 times 2 plus 16 divided by 4 times 2. Now, we don't have any parentheses left, so we don't have to worry about the P in PEMDAS. We have no E, no exponents in this. So then we go straight to multiplication and division. We have a multiplication. We have some multiplication going on there. We have some division going on here, and a multiplication there. So we should do these next before we do this addition right there. So we could do this multiplication. We could do that multiplication. 7 times 2 is 14. We're going to wait to do that addition. We're going to wait to do that addition. And then here we have a 16 divided by 4 times 2. That gets priority of the addition, so we're going to do that before we do the addition. But how do we evaluate that? Do we do the division first? Do we do the multiplication first? And remember, I told you in the last video, when you have multiple operations of the same level, in this case division and multiplication, they're at the same level, you're safest going left to right, or you should go left to right. So you do 16 divided by 4 is 4. So this thing right here simplifies 16 divided by 4 times 2. It simplifies to 4 times 2 times 2. That's this thing in green right there. And then we're going to want to do the multiplication next. So this is going to simplify to, because multiplication takes priority over addition. This simplifies to 8. And so you get 14, this 14 right here, plus 8. And what's 14 plus 8? That is 22. That is equal to 22. And we are done.
Cool. Okay, next. Last. Two-step expression.
If I were to ask you, what is 5 minus 3 plus 2, what would you say that is? Pause this video and try to figure that out. All right, well, if you wanted to tackle this, you would really just read it from left to right, or you would compute it from left to right. You'd first figure out what 5 minus 3 is, and 5 minus 3 is equal to 2. And so you'd say, okay, that's going to be 2 plus 2, which, of course, we know is equal to 4. Now, what if I were to involve a little bit of multiplication or division? If I were to go up to you and I were to say, what is 5 plus 3 times 2? Pause this video and try to figure that out. Well, you might be tempted to do it in a similar way. You might be tempted to say, okay, I'll just go from left to right. I'll first compute what 5 plus 3 is, and that, of course, would be equal to 8. And then I would multiply 8 times 2 to get 16. But it turns out that this would not be the right way to approach this, because for very good reasons that we'll study in perhaps future videos, we don't always go left to right, especially when we're dealing with different types of operations. And the standard way that this is approached is that multiplication and division will be done before addition and subtraction. So the way that you would actually compute this is that you would compute the 3 times 2 first. So you would say that this is the same thing as 5 plus 6. 5 plus 6, which is going to be equal to 11, not 16. So this is going to be equal to 11. So with that out of the way, let's do a few more examples. Let's say someone were to approach you and say, what is 9 minus 6 divided by 3? Pause this video and see if you can figure
it's gonna
that
be
out.
6.
Well, as I just said, we would do multiplication or division before we do subtraction. So we'll actually do the 6 divided by 3 first, and 6 divided by 3 is 2. So this simplifies to 9 minus 2, which is equal to 7. And I really want to emphasize it's important that you get this idea that multiplication and division should be done before the addition or subtraction, unless you're given some other types of directions. Because if you just went left to right here, you would have said 9 minus 6 is 3, and then you would have divided that by 3, which would have given you 1, which is clearly a different number than 7. Let's do one more example just for kicks.
Just for kicks.
Let's say that someone were to ask you, what is 2 times 3 minus 1? Pause the video and try to figure that one out.
That is 5.
Well, in this one, doing our multiplication first is also the same as going left to right first. So if we do 2 times 3 first, 2 times 3 is 6, so that's 6. And then we would want to calculate 6 minus 1, which is, of course, equal to 5. So big picture, if you just have a bunch of things that are being added, subtracted, multiplying, and divided, and there's no parentheses in it, you would always prioritize the multiplication or the division over the addition or the subtraction.
Okay, cool. Now for the activities. Yo, this is insane. We have exponents. It's going to be like plus 9 plus 10. I don't know how many zeros it should be. If this is like 10 squared, like it's gonna be 100, right? So 2 zeros. So the same thing if it, so it's gonna be 10 and with 7 zeros. So it's 7 zeros. It's good. 1, 2, 3, 4, 5, 6, 7 plus 10. Holy shit, I could be wrong. Cool. Okay, cool. Match expression to its exponential form. Yo, why do we have exponents, man? You haven't going to teach me that? No? Okay, cool. Okay, so this 8 minus 4 times 4 is 16. And then I guess this is 16. It's gonna 4 plus 4, 8. Okay, let's kind of cancel each other. No. Oh, this is 16, this is 4, okay. I value the following expression, 1 to the 4th power, okay. How am I supposed to add this? So we have, this is still the same shit. So it's gonna be 16, right? Okay, it's gonna be 6 divided by 3. We get 2 plus 81 minus 4. So we get that. So we have like 83 minus 4. We get 99. Oh, no, oh, it's just 99. Dude, 79. Order the expression from least to greatest. Okay, 8 squared minus 60, it's gonna be 4. It's 11. 4 times 5 is 20. Okay, cool. Value for the expression. So 3 times 3, 9. Let's say 27. Minus 10, we have 17. With 24. It's gonna be 24. I don't know. Cool. Okay. 9 minus. Let's do this first. It's gonna be 27 times 4. Times. Oh wait. Yo, it's 27 times 3, right? Okay. 1, 2, 6, 7, 81. Is it for real? 21. Yeah, it's gonna be 21, 6, 7. Okay. So 9 minus 1 is 8 plus 1 is 17. Yo, for real. So it's gonna be 8. These two things gonna be 17. Then plus 81. Get 98. Yo, I could be wrong. Let's do this again for the last time. 9 minus 1 is 8. Plus 9 is 17. It's 81. 98. Two-step expressions. Oh. Dave tried to evaluate 55 minus 15 plus 20. Step by step. Okay, so 55 minus 15. 40. Plus 20. Yo, 40 plus 20, you get 20. Are you shitting me, Dave? Oh, let's give me 9. Minus 4 is 5. What is the first step to evaluate 55 minus 15 plus 20? 155 minus 15. Bob tried to evaluate 12 plus 8 and divided by 3. So, your first step, you're already wrong in your first step, man. Evaluate. Okay, it's gonna be 40 divided by 5. It's gonna be 8. What is the first step to evaluate? 5 times 6 plus 30. 5 times 6. Joe tried to evaluate 14 minus 6 times 4. Find Joe's mistake. You already made a mistake at your first step. Okay, holy mother of God. Okay, I still have a lot of time, only 30 minutes in. Okay, cool. What if I click the title itself? Whoa, I get
So if you look at each of these 4 by 6 grids, it's pretty clear that there's 24 of these green.
Not used to that view. Should I do it like this? How do you go back to mutilation?
Green circle things in each. So if you look at each of these 4 by 6 grids, it's pretty clear that there's 24 of these green circle things in each of them. But what I want to show you is that you can get to 24 as the product of 3 numbers in multiple different ways. And it actually doesn't matter which products you take first or what order you actually do them in. So let's think about this first. So the way that I've colored it in, I have these 3 groups of 4. If you look at the blue highlighting, this is 1 group of 4, 2 groups of 4, 3 groups of 4. Actually, let me make it a little bit clearer. 1 group of 4, 2 groups of 4, and 3 groups of 4. So these 3 columns you could view as 3 times 4. Now, we have another 3 times 4 right over here. This is also 3 times 4. We have 1 group of 4, 2 groups of 4, and 3 groups of 4. So you could view these combined as 2 times 3 times 4. We have 1 3 times 4, and then we have another 3 times 4. So the whole thing we could view as, let me give myself some more space, as 2 times, let me do that in blue, 2 times 3 times 4. That's the total number of balls here. And you can see it based on how it was colored. And of course, if you did 3 times 4 first, you get 12. And then you multiply that times 2, you get 24, which is the total number of these green circle things. And I encourage you now to look at these other 2, pause the video, and think about what these would be the product of. First looking at the blue grouping, then looking at the purple grouping in the same way that we did right over here. And verify that the product still equals 24.
3, okay.
Well, I assume that you've paused the video. So you see here in this first, I guess you could call it a zone, we have 2 groups of 4. So this is 2 times 4 right over here. We have 1 group of 4, another group of 4. That's 2 times 4. We have 1 group of 4, another group of 4. So this is also 2 times 4 if we look in this purple zone. 1 group of 4, another group of 4. So this is also 2 times 4. So we have 3 2 times 4s. So if we look at each of these, or all together, this is 3 times 2 times 4. So 3 times 2 times 4. 2 times 4. Notice I did a different order, and I'm here I did 3 times 4 first. Here I'm doing 2 times 4 first. But just like before, 2 times 4 is 8. 8 times 3 is still equal to 24, as it needs to, because we have exactly 24 of these green circle things. Once again, pause the video and try to do the same here. Look at the groupings in blue, then look at the groupings in purple, and try to express these 24 as a product of some kind of product of 2, 3, and 4. Well, you see first we have these groupings of 3. So we have 1 grouping of 3 in this purple zone, 2 groupings of 3 in this purple zone. So you could view that as 2 times 3. And we have 1 3 and another 3. So in this purple zone, this is another 2 times 3. We have another 2 times 3. Whoops, I wrote 2 times 2. 2 times 3. We have another 2 times 3. 2 times 3. And then finally we have a fourth 2 times 3. So how many 2 times 3's do we have here? Well, we have 1, 2, 3, 4 2 times 3's. So this whole thing could be written as 4 times 2 times 3. 2 times 3. Now what's this going to be equal to? Well, it needs to be equal to 24, and we can verify 2 times 3 is 6 times 4 is indeed 24. So the whole idea of what I'm trying to show here is that the order in which you multiply does not matter. How you associate it, let me make this very clear. So whether you do, let me pick a different example, a completely new example. So let's say that I have 4 times 5 times 6. You can do this multiplication in multiple ways. You could do 4 times 5 first, or you could do 4 times 5 times 6 first. And you can verify that. I encourage you to pause the video and verify that these two things are equivalent.
Yeah, they are both.
And this is actually called the associative property. It doesn't matter how you associate these things, which of these that you do first. Also, order does not matter, and we've seen that multiple times. Whether you do this or you do 5 times 4 times 6, notice I swapped the 5 and 4, this doesn't matter. Or whether you do this or 6 times 5 times 4. Doesn't matter. Here I swapped the 6 and the 5 times 4. All of these are going to get the exact same value, and I encourage you to pause the video. So when we're talking about which one we do first, whether we do the 4 times 5 first or the 5 times 6, that's called the associative property. It's kind of a fancy word for a reasonably simple thing. And when we're saying that order doesn't matter, when it doesn't matter whether we do 4 times 5 or 5 times 4, that's called the commutative property. And once again, fancy word for a very simple thing, just saying it doesn't matter what order I do it in.
Commutative. Fancy word for a simple thing.
We want to figure out how many balloons we have here, and obviously we could just count these.
Properties.
We do 4 times all these. Also 6, notice swap the 6 and the 5 times 4. All of these are going to get the exact same value, and I encourage you to pause the video. So when we're talking about which one we do first, whether we do the 4 times 5 first or the 5 times 6, that's called the associative property. It's kind of a fancy word for a reasonably simple thing. And when we're saying that order doesn't matter, when it doesn't matter whether we do 4 times 5 or 5 times 4, that's called the commutative property. And once again, fancy word for a very simple thing, just saying it doesn't matter what order I do it in. Count these, but now we have other ways of thinking about it, especially because they're arranged in this. We want to figure out how many balloons we have here, and obviously we could just count these, but now we have other ways of thinking about it, especially because they're arranged in this nice array, this nice grid pattern here. And the reason why it's useful to not just always have to count it, but to be able to use a little bit of multiplication with the number of rows and the number of columns, is that you might run into things, or you will run into things, where it's very hard to count each of the objects individually, but it might be a little bit easier to count the rows and to count the columns. So for example, right over here, we see that we have 1, 2, 3, 4 rows, and we have 1, 2, 3, 4, 5, 6, 7 columns. So this is you could view this as an array of objects where we have 4 rows. Let me write that down. We have 4 rows and we have 7 columns. 7 columns. And you might already remember that we can calculate the total number of objects by multiplying the rows times the columns. 4 rows times 7 columns. Now why does this work? Why will this give us the actual number of objects? Well, we could view this. We have 4 rows, so we have 4 groups of things. And how many things are in each of those rows? Well, the number of columns. We have 7 things in each of those 4 rows. So 4 groups of 7. Or you could view it the other way around. You could view that each column is a group. So then you have 7 groups. And how many objects do you have in each? Well, that's what the rows tell you. You have 4 things in each of those columns. And we already know that both of these quantities are going to find the exact same number, the number of things that we have right over here. So these two things are equivalent. 4 times 7 is equal to 7 times 4. And there's a bunch of ways that we can calculate either one of these. We can skip count by 4. We say 4 times 4, 8, 12, 16, 20, 24, 28, and let's see, let me make sure that's 7. So 4 times 1, 2, 3, 4, 5, 6, 7. So we get 28. We could just calculate there are 28 objects here. And likewise, we could skip count by 7s. We could go 7 times 2 is 14, times 3 is 21, times 4 is 28, just adding 7 every time. And so we could get 28 the other way. Let's do that in that same color. We could get 28 the other way. But what if you had a situation where you didn't know, where you either didn't want to do these techniques or it would have been hard to do these techniques, or you didn't know what 4 times 7 was off of the top of your head, which you should know at some point in the very, very near future. Is there any way to break this down into something that maybe you do know, or maybe that's a little bit easier to compute? Well, you could realize that 7 columns is the same thing as 5 columns and then 2 columns. So you could view 7 columns as, you could view it as 5 columns. So this is 5 columns right over here, plus 2 columns, plus, use another color, plus 2 columns. So that's just like saying that 4 times 7, we do the 7 in that purple color, want to stay color coded, is the same thing as 4 times 5 plus 2. 5 plus 2. And all I did is I replaced the 7 with a 5 plus 2. The 7 has been replaced with the 5 plus 2. Now why is this interesting? Well, now I can break this up into 2 separate arrays. So I could say, well, look, there's the array that has 4 rows and 2 columns right over here. And then there's the array that has 4 rows and 5 columns right over here. So how many objects are in this one, in the yellow one right over here?
20.
Well, there's 4 times 5. 4 times 5 objects. So there's 4 times 5 objects in the yellow grid or yellow array. And how many in this orangish looking thing? Well, there's going to be 4 times 2. 4 times 2. 4 times 2. And if we take the sum of the 4 times the 5 and the 4 times the 2, what are we going to get? Well, we're going to get the 4 times the 7. We're going to get the 4 times the 5 plus 2. So if we take the sum of these things, and we want to do the multiplication first, so I'll just put a parenthesis around that to emphasize that this is going to be the same thing as these things up here. And so you might say, oh, I know what 4 times 5 is. 4 times 5 is 20. 4 times 5 is 20. 4 times 2 is 8. 20 plus 8 is 28. And you might say, okay, Sal, that was kind of a, I get it. 4 times 7 is 28. 4 times, which is the same thing as 4 times 5 plus 2. And then I see that that's the same thing as 4 times 5 plus 4 times 2. And actually, this is called the distributive property, that 4 times 5 plus 2 is the same thing as 4 times 5 plus 4 times 2. But, I could just do one of these first techniques you talked about. Why is this distributive property that you just showed me, why is this useful for computing or doing multiplication problems? Well, let me give you a slightly more difficult one. Let's imagine you wanted to multiply 6 times,
so like I'm gonna
6
do 6 times 30
let's
first.
write it as 6 times
Plus 6
36.
times 6.
And actually, I don't need to write that parentheses.
Okay.
6 times 36.
36.
So how could you do this? Well, you could decompose 36 into 2 products, or into 2 numbers where it's easier to find the product of that and 6. So for example, 36 is the same thing as 30 plus 6. So this is going to be equal to 6 times 30 plus 6. 6 times 30 plus 6. And what's this going to be? Well, we just saw 6 times these two things added together first. This is going to be equal to, 6 times 30, 6 times 30, 6 times 30, plus 6 times 6, plus 6 times 6, 6 times 6. Notice, we distributed the 6. 6 times 30 plus 6 times 6. Now, why is this useful? Why was this useful at all? I'm going to put parentheses to emphasize. We're going to do the multiplication first. In general, when you see multiplication and addition in a row like this, and division, you want to do your multiplication and division first, then do your addition and subtraction. So what's 6 times 30? Well, this is easier to calculate. 6 times 3 we know to be 18, so 6 times 30 is going to be 180. And 6 times 6, well, we know that's going to be 36. So this is going to be 180 plus 36. And what's that going to be? 180 plus 36. Well, 0 plus 6 is 6. 8 plus 3 is 11. 1 plus 1 is 2. So you just figured out that 6 times 36 is equal to 216. And what we just did with the distributive property, this is actually going to be how you're going to multiply all sorts of larger numbers, way larger than what we just saw. So the distributive property, which hopefully you're pretty convinced by based on how we broke things up, is a super useful thing as you want to compute larger and larger numbers, and you're going to find it even more useful when you go even further in your mathematical career.
Use the commutative law of addition. Let me underline that. The commutative law of addition to write the expression 5 plus 8 plus 5 in a different way and then find the sum. Now, this commutative law of addition sounds like a very fancy thing, but all it means is if you're just adding a bunch of numbers, it doesn't matter what order you add the numbers in. So we could add it as 5 plus 8 plus 5. We could order it as 5 plus 5 plus 8. We could order it 8 plus 5 plus 5. These are all going to add up to the same things. And it makes sense. If I have 5 of something and then I add 8 more and then I add 5 more, I'm going to get the same thing as if I had took 5 of something, then added the 5, then added the 8. And you could try all of these out. You'll get the same thing. Now, they say in a different way and then find the sum. The easiest one to find the sum of, actually, let's do it all of them, but the easiest one, just because a lot of people immediately know that 5 plus 5 is 10, is to maybe start with the 5 plus 5. So if you have 5 plus 5, that's 10. Plus 8 is equal to 18. Now let's verify that these two are the same exact thing. Up here, 5 plus 8 is 13. 13 plus 5 is also 18. That is also 18. If we go down here, 8 plus 5 is 13. 13 plus 5 is also equal to 18. So no matter how you do it, no matter what order you do it in, and that's the commutative law of addition. Sounds very fancy, but it just means that order doesn't matter if you're adding a bunch of things. Use the commutative law of multiplication. The commutative law of multiplication. To write 2 times 34 in a different way. Simplify both expressions to show that they have identical results. So once again, this commutative law just means that order doesn't matter. It sounds very fancy. Commutative law of multiplication. But all that says is it doesn't matter whether we do 2 times 34 or whether we do 34 times 2. The order does not matter. We can commute the two terms. Both of these are going to get you the same exact answer. So let's try it out. What is 2 times 34? And we could write it like this, literally. You'll almost never see it written like this, but it is literally 2 times 34. Almost always people write the larger digit on top, or the digit with more digits, or the number with more digits on top. But let's do it this way. 4 times 2 is 8. And then we'll put a 0. 3 times 2 is 6. Or you could view it as 30 times 2 is 60. Add them together. 8 plus 0 is 8. 6, bring it down. It's not being added to anything. You get 68. So 2 times 34 is 68. Now if you do 34 times 2, if we were to do 34 times 2, 2 times 4 is 8. 2 times 3 is 6. That's why it's always nicer to write the number with more digits on top. It also is equal to 68. So it doesn't matter whether you have 2 groups of 34 or 34 groups of 2. In either case, you're going to have 68.
In this video, we're going to talk about one of the most important ideas in mathematics, and that's whether order matters when you multiply two numbers. So, for example, is 3 times 4 the same thing as 4 times 3? Are these two things equal to each other? And regardless of whether these two are equal to each other, is it always the case that if I have some number times some other number, if I swap the order, am I going to get an equivalent number? Well, pause this video and see if you can work through that. Try to think about that a little bit before we think through it together. Well, let's think through this particular example, and we're going to do so with the help of some angry cats. So we clearly see some angry cats here. Meow. Yes, they are angry. We could view this as 3 groups of 4. So this is one group right over here of angry cats, 4 angry cats. This is 2 groups of 4 angry cats. And this is 3 groups of 4 angry cats.
So relaxed.
If we view the first number here as groups of the second number. But we could also view it as 4 groups of 3. How would we do that? Well, we could have one group of 3 angry cats. We can have 2 groups of 3 angry cats. We can have 3 groups of 3 angry cats. And we can, of course, have 4 groups of 3 angry cats. So based on that, if you think of it, the first number as groups of the second number, well, it seems like the order doesn't matter. Another way you could think about it is, here you have 4 rows of 3 angry cats. You have 1, 2, 3, 4 rows of 1, 2, 3 angry cats. And so to figure out how many total cats you have, you multiply 4 times 3. But you could view this same group of angry cats, but just view it with a slightly different perspective. So here we have our angry cats. And then let me rotate our angry cats, probably risking making them a little bit angrier. Let me move them back in. And now we could view this as 3 rows, 1, 2, 3, of 4 cats in each row. So let me put all of these upright. So we have 1, 2, 3 rows of 1, 2, 3, 4 cats. Don't want to look at those because it might make us a little bit confused. And we're dealing with the exact same number of cats. And so I'm only dealing with 3 and 4 here. But what you will see is order doesn't matter when you are multiplying two numbers. And we could also see that on a number line. And we could do that with multiple examples. I'll keep a couple of angry cats here looking at us just to keep us in check. If we want to think about 3 times 4, we could view it as 4 threes. So 3, 6, 9, 12. Or we could view it as 3 fours. 4, 8, and 12. And I've focused a lot on 3 and 4, but we could do it with any two numbers that we're trying to multiply together. So let's say we wanted to do that with, I don't know, let's see 6, whether 6 times 4, whether it's the same thing as 4 times 6. Well, you could view it as 6 fours, 4, 8, 12, 16, 20, and then 24. Or you could view it as 4 sixes. 1 6, 12, 18, and 24. So big takeaway, order doesn't matter when you are multiplying numbers like this. And this is sometimes referred to as the commutative property. It's a fancy word, but it's really just saying that whether you're doing 6 times 4 or 4 times 6, the commutative property of multiplication says, hey, those two things are going to be equivalent. Meow. Yes, they are angry for being rotated.
Copy video URL.
In this video,
This guy, I died.
Yes, they are angry. We
Okay.
in this video,
Commutative property of multiplication. Mathematical says order in which you does not change the product. It's true. Yeah, want to learn more about? Yeah, we've done that. Okay, next video. Associative Law.
Use the Associative Law of Addition to write the expression, and we have, let's see, a 77 plus 2 in parentheses plus 3 in a different way. Simplify both expressions to show they have identical results. So this Associative Law of Addition, which sounds very fancy and complicated, literally means that you can associate these three numbers in different ways, or you can add them in different orders. Now let me just make that clear. So the way they wrote it right here, they wrote 77 plus 2 in parentheses, and then they wrote plus 3. These parentheses mean do the 77 plus 2 before you add the 3. So if you were to evaluate this, you would evaluate what's in the parentheses first. So you would say, well, 77 plus 2, that's 79. So everything in the parentheses just evaluates to 79. And then you still have that plus 3. And 79 plus 3 is 82. So this is equal to 82. That's if you just evaluate it the way that they gave it to us. Now, the Associative Law of Addition tells us it doesn't matter whether we add 77 and 2 first or whether we add 2 and 3 first. We can associate them differently. So this is going to be the exact same thing. This is the exact same thing as, we could write it this way. So let me write them all. 77 plus 2 plus 3. If we have no parentheses here, this is actually the same thing as this over here, because we'd go 77 plus 2 is 79, plus 3 is 82. But the associative law tells us, well, you know what? I could do 77 plus 2 plus 3. I could add this first and then add it to 77. And it's going to be the exact same thing as if I add these two guys first and then add the 3. And let's verify that for ourselves. So 2 plus 3 is 5. So this evaluates to 77 plus 5. 77 plus 5. And 77 plus 5, once again, is 82. Is 82. So it doesn't matter how you associate the numbers. Either way, you get 82. And that's the Associative Law of Addition. Use the Associative Law of Multiplication to write, and here they have 12 times 3 in the parentheses, and then they want us to multiply that times 10 in a different way. Simplify both expressions to show they have identical results. So the way that they wrote it is, let me just rewrite it. So they have 12 times 3 in parentheses, and then they multiply that times 10. Now, whenever something is in parentheses, that means do that first. So this literally says, let's do the 12 times 3 first. Now, what is 12 times 3? It's 36. So this evaluates to 36, and then we still have that times 10 over there, times 10. And we know the trick. Whenever we multiply something times a power of 10, we just add the number of zeros that we have at the back of it. So this is going to be 360. This is going to be equal to 360. Now, the Associative Law of Multiplication, once again, sounds like a very fancy thing. All that means is that it doesn't matter how we associate the multiplication, or it doesn't matter how we put the parentheses, we're going to get the same answer. So let me write it down again. If we were to do 12 times 3 times 10, if we just wrote it like this without parentheses, if we just went left to right, that would essentially be exactly what we just did here on the left. But the Associative Law of Multiplication says, you know what? We can multiply the 3 times 10 first and then multiply the 12. And we're going to get the exact same answer as if we multiply the 12 times the 3 and then the 10. So let's just verify it for ourselves. So 3 times 10. 3 times 10 is 30. and we still want to multiply the 12 times that. And what's 12 times 30? And we've seen this several times before. You can view it as a 12 times 3, which is 36, but we still have this 0 here. So that is also equal to 360. So it didn't matter how we associated the multiplication. You can do the 12 times 3 first, or you can do the 3 times 10 first. Either way, they both evaluated to 360.
So what we're going to do is get a little bit of practicing multiple numbers together, and we're going to discover some things. So first, I want you to figure out what 4 times 5 times 2 is. Pause the video and try to figure it out on your own. All right, so whatever your answer is, some of you might have done it this way. Some of you might have said, hey, what is 4 times 5? And then you multiplied it by 2. So what you would really have done is, you would have done 4 times 5 first. That's why I put parentheses around that. And then you would have multiplied by 2. And what would you have gotten? Well, the 4 times 5 part, that is, of course, 20. And then you multiply that times 2, and you would get 40, which, of course, would be correct. 4 times 5 times 2 is indeed equal to 40. Now, what I want you to do now is, as quickly as possible, try to figure out what 5 times 2 times 4 is. Really quick, pause the video, try to figure that out. Well, some of you might have tried, and you might have done it in a similar way, where you tried to figure out what 5 times 2 is first. And you said, okay, 5 times 2 is equal to 10. And then I'd multiply that times 4. And then you would say, well, gee, this is the same thing as I got last time. Is there something interesting going on? And the interesting thing that you might realize is, in both cases, we're multiplying the same 3 numbers. We are just doing it in a different order. Here we multiplied 4 times, we wrote it out in a different order, 4 times 5 times 2. Here we wrote 5 times 2 times 4. Here we did the 4 times 5 first. Here we did the 5 times 2 first. But notice, we got the same result. And I encourage you, pause this video, try to multiply these numbers in any order. Maybe you do 2 times 4 first. In fact, let's just do that. Let's do 2 times 4, and then multiply that by 5. What is this going to be equal to? Well, you might notice again, this is 2 times 4 is 8. You multiply that times 5. Well, once again, we got 40. So you might see a pattern here. It doesn't matter which order we multiply these things in. In fact, you could write 4 times 5 times 2. You could do the 4 times 5 first, 4 times 5 times 2. Or you could do 4 times 5 times 2. So you could do 4 times 5 times 2. So it doesn't matter which order you multiply these things in. In every case, you are going to get 40. Now, there's a very fancy term for this, the associative property of multiplication. But the main realization is, and it's not just true with 3 numbers. In fact, you've seen something similar with 2 numbers, where it doesn't matter what order you multiply them in. But what you see is with 3 numbers, and even if you tried it with 4 or 5, or really 1,000 numbers being multiplied together, as long as you're just multiplying them all, it doesn't matter what order you're doing it with. And it doesn't matter in what order you associate them with. Here we did 4 times 5 first, 4 times 5 first. Here we did 5 times 2 first. But in either case, we got the same result. And I encourage you, after this video, try to draw it out. Try to think about why that actually makes intuitive sense, why this is true in the world. And it's nice because it simplifies our life when we're doing mathematics, not only now, but in our future mathematical career. In this video, we're going to think about how we can use our knowledge of multiplying single-digit numbers to multiply things that might involve 2 digits. So, for example, let's start with, what is 5 times 18? And you can pause the video and see how you might try to approach this, and then we'll do it together. All right, so if we're trying to tackle 5 times 18, one strategy could be to say, hey, can I re-express 18 as the product of 2 numbers? And the one that jumps out at me is that 18 is the same thing as 2 times 9. And so I could rewrite 5 times 18. This is the same thing as 5 times, instead of 18, I could write 2 times 9. Now, why does this help us? Well, instead of multiplying the 2 times 9 first to get the 18 and then multiplying that by 5, what we could do is we could multiply the 5 times the 2 first. And you might be thinking, wait, hold on a second. Before, you did the 2 times 9 first, and now you're telling me that you're going to change the order, that you're going to say, hey, let's multiply the 5 times 2 first. Is that okay? And the simple answer is yes, it is okay. If you are multiplying a string of numbers, you can do them in any order that you choose. And so this is often known as the associative property of multiplication. We can associate the 2 with the 9 first. We can multiply those first. Or we can have an association with the 5 and the 2. We can multiply those two first. Now, why is that helpful? Well, what is 5 times 2? Well, that's pretty straightforward. That's going to be equal to 10. So this is going to be equal to 10, in that same color, 10 times 9. Now 10 times 9 is a lot more straightforward for most of us than 5 times 18. 10 times 9 is equal to 90. Let's do another example. Let's say we want to figure out what 3 times 21 is. Pause this video and see if you can work through that. There's multiple ways to do it, but see if you could do it the way we just approached this first example. Well, as you could imagine, we want to re-express 21 as the product of smaller numbers. So we could rewrite 21 as 3 times 7 maybe. And so if we rewrite it as 3 times 7, and now we do the 3 times 3 first. So I'm going to just put parentheses there, which we can do because of the associative property of multiplication, fancy word for something that is hopefully a little bit intuitive. Well, then this is going to be equal to, what's 3 times 3? It is 9. And then times 7, which you may already know is equal to 63. Let's do another example. This is kind of fun. Let's say we want to figure out what 14 times 5 is. Pause this video and see if you can figure that out.
I can do the 15 to
Well, we could once again try to break up 14 into the product of smaller numbers. 14 is 2 times 7, so we can rewrite this as 2 times 7, or 7 times 2. And I'm writing it as 7 times 2 because I want to associate the 2 with the 5 to get the 10. Times 5.
Yeah, it's pretty cool.
And then I could multiply the 2 times 5 first. And so this is going to give us 7 times 10. 7 times 10, which is, of course, equal to 70. One more example. Let's say we want to calculate 15 times 3. How would you tackle that? Well, we can break up 15 into 5 times 3. 5 times 3, and then we can multiply that, of course, by this 3. And then we can multiply the 3's together first, and then this amounts to 5 times 9. And 5 times 9, you might already be familiar with this. This is going to be equal to 45. And another way to get to 45, you could say, hey, 5 times 10 is 50, so 5 times 9 is going to be 5 less than that, which is also 45.
The associative property is a math rule that the way in which factors are grouped in the does not change the product. It's associative, yeah. Which expression are equivalent to 9 times 8 times 5? Multiply. Find the products. Okay. That's 6 times 5, 30, and both 30, yeah. 15 times 2 is 30 as well. Complete the equation to solve in different ways. Aaron tried to find Aaron's mistake. Aaron. Yo, Baltimore accent. Earn. Identity property of 1.
We're asked to multiply 65 times 1. So literally, we just need to multiply 65, and we could write it as a times sign like that, or we could write it as a dot like that. But this means 65 times 1. And there's two ways to interpret this. You could view this as the number 65 one time, or you could view this as the number 1 65 times, all added up. But either way, if you have 165, this is literally just going to be 65. Anything times 1 is going to be that anything. Whatever this is, whatever this is times 1 is going to be that same thing again. If I have, you could think of, well, if I had just some kind of placeholder here, times 1, and I could even write it as the times symbol, times 1, that's going to be that same placeholder. That's going to be that same placeholder. So if I have 3 times 1, I'm going to get 3. If I have 5 times 1, I'm going to get 5. Because it's literally, all this is saying is 5 one time. If I put, I don't know, 157 times 1, that'll be 157. I think you get the idea.
Yep.
Evaluate 0 plus y plus negative 7 when y is equal to negative 3, y is equal to 0, and y is equal to 7. So let's take the first situation where y is equal to negative 3. Then this expression right here would be 0 plus negative 3, because that's our y now, plus negative 3 plus negative 7 plus negative 7. Now, 0 plus or minus anything won't change its value. So you can really just ignore the 0 here. So this is going to be the same thing. This is going to be the exact same thing as negative 3 plus negative 7 plus, it's a different color, plus negative 7. Negative 3 plus negative 7. And now we could draw a number line here just to help us visualize it. But even if you didn't have the number line, you would say, look, we're already 3 below 0. We're going to go another 7 to the left. We're going to go another 7 more negative. So if we're 3 away from 0, we're going to go 7 more away from 0. So we're going to be 10 to the left of 0, or negative 10. Or another way to think about it, let me draw the number line there. Always better to have a visual. So we're starting, so this is 0. We're starting at negative 3. We're starting at negative 3. And to that, we're adding negative 7. So we're starting at negative 3. The absolute value is negative 3 at our starting point. To that, we're adding another negative 7. We're going to move negative 7 to the left. So we're adding, let me draw this. We're adding a negative 7 right over here. We're adding a negative 7 right over here. So what's the length of this right over here? The absolute value. We're adding at negative 3. The absolute value is negative 3 at our starting point. To that, we're adding another negative 7. We're going to move negative 7 to the left. So we're adding, let me draw this. We're adding a negative 7 right over here. We're adding a negative 7 right over here. So what's the length of this right over here? The absolute value of negative 7 is equal to 7. That's the length of this arrow, but we're moving it to the left. The length of this arrow right here, the absolute value of negative 3 is 3. So we're already 3 to the left. Now we're moving 7 more to the left. So now we're going to be 10 to the left. We are going to be 10 to the left. 10 to the left. This is literally, this is equal to the absolute value of negative 7. This is, let me do it in the order that we wrote it in the problem. So this is equal to the absolute value of negative 3. You want to use the same colors. The absolute value of negative 3 plus the absolute value of negative 7 plus the absolute value of negative 7. Negative 7. But we're to the left. We're to the left of 0. We've been moving to the left. So it's the negative of that, which is negative 10. So if your signs are the same, you can just kind of take the absolute values of them. Say, OK, that's how far we're going to move total. And we're that far away from 0 to the left, since everything was a negative number. So the answer here is negative 10. So that was y is equal to negative 3. Let's think about when y is equal to 0. When y is equal to 0, this expression up here becomes 0 plus 0. Our y here is going to be 0 do that in that same blue color. Plus 0 plus negative 7. Plus negative 7. Now, you add 0 to anything, it's not going to change the value. So this thing right over here, this is pretty straightforward. These don't matter. It's just going to be equal to a negative 7. Now let's do the last one, when y is equal to 7. So our expression is going to be 0 plus, our y is equal to 7. So 0 plus 7, and then we have a plus a negative 7. Plus a negative 7. Now there's a couple of ways to do this. You could literally just say, well, adding a negative number is equivalent to subtracting the number. You could say this is equivalent to 0 plus 7 minus 7. Plus negative 7 is the same thing as subtracting a 7. The 0 doesn't matter, so this is equal to 7 minus 7, which is equal to 0. Another way to think about it, let's draw a number line. Let's draw a number line. So let's say that this is 0. We're starting off at 7. So we're starting off at 7. We're 7. We are 7 to the right of 0. And to that, we are adding a negative 7. So to that, we're going to add a negative 7. So we're going to move to 7 to the left of where we were. 7 to the left of 7, which was 7 to the right of 0. So this gets us back to 0 over here. So the answer is 0.
Cool. Okay. Holy crap, 2 more videos and 2 articles. And oh my gosh, this is... Okay, cool. Well, that's a lot, but
let's say that we have the number 5, and we're asked, what number do we add to the number 5 to get to 0? And you might already know this, but I'll just draw it out.
Inverse
so let's say we have a number line right over here, and 0 is sitting right over there, and we are already sitting here at 5. So to go from 5 to 0, we have to go 5 spaces to the left. We have to go 5 spaces to the left. And if we're going 5 spaces to the left, that means that we are adding negative 5. So if we add negative 5 right here, then that is going to get us back to 0. That is going to get us back right over here to 0. And you probably already knew this. And this is a pretty maybe common sense thing right here, but there's a fancy word for it called the additive inverse property. And all the additive, I'll just write it down. I think it's kind of ridiculous that it's given such a fancy word for such a simple idea. Additive inverse property. And it's just the idea that if you have a number and you add the additive inverse of the number, which is what most people call the negative of the number, if you add the negative of the number to your number, you're going to get back to 0 because they have the same size. You could view it that way. They both have a magnitude of 5, but this is going 5 to the right, and then you're going 5 back to the left. Similarly, if you started, let me draw another number line right over here. If you started at negative 3, if you're starting right over here at negative 3, so you've already moved 3 spaces to the left, and someone says, well, what do I have to add to negative 3? What do I have to add to negative 3 to get back to 0? Well, I have to move 3 spaces to the right now, and 3 spaces to the right is in the positive direction, so I have to add positive 3. So if I add positive 3 to negative 3, I will get 0. So in general, if I have any number, if I have 1,725,314, and I say, what do I need to add to this to get back to 0? Well, I have to essentially go in the opposite direction. I have to go in the leftwards direction. So I'm going to subtract the same amount, or I could say I'm going to add the additive inverse, or I'm going to add the negative version of it. So this is going to be the same thing as adding negative 1,725,314, and that'll get me back to 0. Similarly, if I say, what number do I have to add to negative 7 to get to 0? Well, if I'm already at negative 7, I have to go 7 to the right, so I have to add positive 7. And this is going to be equal to 0. And this all comes from the general idea 5 plus negative 5, 5 plus the negative of 5, or 5 plus the additive inverse of 5, you can just view this as another way of 5 minus 5. And if you have 5 of something and you take away 5, you've learned many, many years ago that that is just going to get you to 0.
Oh, yeah.
Let's say that I have 5 lemons. So
Inverse
that's
property
1,
of
2,
multiplication.
3, 4, 5 lemons.
0.
And I were to ask you, what do I have to multiply times 5 to get 1? Or in this case, what do I have to multiply times 5 lemons to get 1 lemon? And so another question you might ask, because really multiplication and division are two sides of the same coin, is what would I have to divide 5 by to get to 1 lemon or yellow circle or whatever I've drawn right over here? Well, if you have 5 things and if you divide by 5, you're going to have 5 groups of 1. So if you divide by 5, you're going to have 1, 2, 3, 4, 5 groups. So you could say 5 divided by 5 is equal to 1. You don't take 5 things divided into 5 groups. Each group is going to have 1 in them. Or you could say 5 times 1/5 is equal to 1. And I used the dot for multiplication. I could also say 5 times 1/5 is equal to 1. These are all really saying the same thing. Maybe what's kind of interesting here, although it's not some huge learning, it's really just another way of writing what you've already probably known, is this idea that if I have a number and I multiply times its multiplicative inverse, and most of the time when people talk about inverses in mathematics, they're talking about the multiplicative inverse, then I'm going to get 1. So 5 times 1/5 is equal to 1, but that's the same. That's just because 5 times 1/5 is the same thing as 5 divided by 5. If you were to actually multiply this out, if you actually take 5 times 1/5, this is equal to 5 over 1 times 1 over 5. You multiply the numerators, 5 times 1 is 5. Multiply the denominators, 1 times 5 is 5. So you have 5/5. And 5/5 is the exact same thing as 1. So if someone were to ask you a question, they said, hey, I have the number 217, and I want to multiply it by something, and I want to get 1 after multiplying it by that something. Well, you say, well, look, if I took 217 and I divided by 217, that would get me to 1. And dividing by 217 is the exact same thing as multiplying by 1 over 217. Multiplying by its multiplicative inverse, which is, once again, a word that is fancier than the actual concept. You're just multiplying by the inverse of this number. Another way to think about it is if I have 5 things, and if I were to take 1/5 of those 5 things, how many things do I have? Well, if I take 1/5 of 5 things, I have exactly 1 thing right over here. But the general idea is super duper duper simple. If I have some crazy number, 8,345, that's actually not so crazy. Let's turn into something in the millions. And 271. So 8,345,271. And I say, what do I have to multiply that? And I'll use this multiplication symbol right now. What do I have to multiply that by in order to get 1? Well, I just have to multiply by the inverse of this, the multiplicative inverse of this. So 1 over 8,345,271.
In this part, we'll learn the 3 main properties of addition. Here's a quick summary of these concepts. Commutative property of addition. Changing the order of addends does not change the sum. Associative property of addition. Changing the grouping of addends does not change the sum. Okay. Commutative is like the orders, right? And associative is the groupings. Okay. The sum of 0 is the numbers. Property of addition. Notice how both sums are, yeah. The multiplication properties. 3 main properties. Here's, hey, where's your distributive? There's no distributive. Changing the order of fraction to factors does not change the product. Changing the groupings does not change the product. The product of 1 and any number is this number, okay. Yeah. Or this is changing the grouping does not change the product. It's 12 and 4, yeah. Which of this is an example of associative property multiplication? This one is grouping. That's 1. Doesn't matter. It doesn't matter if 1 comes before or after a number. Here's an example of it. Yeah. Not gonna do the videos. We're gonna do the practice. Okay, cool. Commutative property, man. Commutative. Commutative is the order, right? And associative is the grouping. Cool. Represent the commutative property of multiplication. Represent 7 times 6. I choose 2 answers, so yeah. We can jump like 7 times, or we can jump like 6 times. 7 times by 6. Which two expressions the following number line? That's 4 times 5 times 4. 4 times 5. 4. Vic has 12 plates. What are 2 ways Vic can stack her plates? 2 stacks of 6 plates and 6 stacks of 2 plates. Which 2 pictures can we represent we use to represent 5 times 2? This is 5 times 2. This is 2 times 5. Wait, what? Yeah, cool. Understand a commutative property. Commutative is the order still, right? Or 4 reasons. Who is correct? Kim says the image represents 4 times 7, or 4 groups of 7. Joe says the image represents 7 times 4, or 7 groups of 4. They're both correct. John says the image is 4 times 8, or 4 groups of 8. What is another way Jenny represents 8 times 4? Zoe has 4 bags of apples. There are 6 apples in each bag. So I multiplied 4 times to find out which number is 6 or 6 times 4. The garden is 8 pots. There are 2 flowers in each pot. Mark multiplied 8 times 8 to find the total number of flower pots. Wait, flowers. Wait, what? There are 2 flowers in each pot. Emma multiplied 2 times 8 to find the total number of flowers. What is this? It's similar. Okay, only Emma's correct. What's this? What is this? Insane! That video is so long. It took me an hour. Crap. Complete the equation. Okay, it's only 2, right? Understand associative property of multiplication. It's gonna be the grouping thing. Okay, so it's gonna be 8. No, which 2 expressions are equivalent? 7 times 3 times 3. Let's do guys. What's this? 2 times 4. 12 times 4 we have 6, right? Okay. Use associative property to multiply two-digit number by 1 digit. Associative. Okay, 2 times 18 is 6. Oh shit, what is this? I don't know the answer to this. Holy crap, it's 56, I don't know. If this is 20, it's 40. Oh shit, it's actually 9 times 4, 36. I'm an idiot. Wow. Okay. 7 times 2 is 7 times 2 is 14, or we can do like 2 times 3 is 6 and 42. Yo. 2, 10, 90. 5 times 5, 6, 16. Associative property of multiplication. Complete the equation to solve 2 times 5 times 4 two different ways. Kim tried to evaluate an expression step by step. Find Kim's mistake. 10. Why is this plus 4? Are you kidding me, Kim? Find product. 14 times 3. Holy shit. It's 14 times 3. It's 42. Complete the equation solved in 2 different ways. 6, 42. What's this? 21. 140. Okay, cool. Ram tried to evaluate experience step by step. Find Ram's mistake. He did not make any mistake. Ram's good. 6 times 30 times 10. 30, okay. So 2 different ways. Oh, cool. Okay. Next, iodized applied to
rewrite the expression 4 times, and then in parentheses we have 8 plus 3 using the distributive law of multiplication over addition. Then simplify the expression. So let's just try to solve this or evaluate this expression, and then we'll talk a little bit about the distributive law of multiplication over addition, usually just called the distributive law. So we have 4 times 8. 4 times 8 plus
44. We can say also
8
11
plus
times 4,
3.
44.
8 plus 3. Now there's 2 ways to do it. Normally when you have parentheses, your inclination is, well, let me just evaluate what's in the parentheses first, and then worry about what's outside of the parentheses. And we can do that fairly easily here. We can evaluate what 8 plus 3 is. 8 plus 3 is 11. So if we do that, let me do that in this direction. So if we do that, we get 4 times, and in parentheses, we have an 11. 8 plus 3 is 11. And then this is going to be equal to, well, 4 times 11 is just 44. So you can evaluate it that way, but they want us to use the distributive law of multiplication. We did not use the distributive law just now. We just evaluated the expression, we used the parentheses first, then multiplied by 4. In the distributive law, we multiply by 4 first. And it's called the distributive law because you distribute the 4, and we're going to think about what that means. So in the distributive law, what this will become, it'll become 4 times 8 plus 4 times 3. And we're going to think about why that is in a second. So this is going to be equal to 4 times 8 plus 4 times 3. 4 times 3. A lot of people's first instinct is just to multiply the 4 times the 8. But no, you have to distribute the 4. You have to multiply it times the 8 and times the 3. This is right here. This is the distributive property in action right here. Distributive property in action. And then when you evaluate it, I'm going to show you in kind of a visual way why this works. But then when you evaluate it, 4 times 8, this is in a different color, 4 times 8 is 32. And then so we have 32 plus 4 times 3. 4 times 3 is 12. And 32 plus 12 is equal to 44. That is also equal to 44. So you can get it either way. But when they want us to use the distributive law, you would distribute the 4 first. Now let's think about why that happens. Let's visualize just what 8 plus 3 is. So let me draw 8 of something. So 1, 2, 3, 4, 5, 6. Let me draw it this. Well, 6, 7, 8, right? 1, 2, 3, 4, 5, 6, 7, 8. And then we're going to add to that. We're going to add to that 3 of something, of maybe the same thing. 1, 2, 3. So you can imagine this is what we have inside of the parentheses. We have 8 circles plus 3 circles. Now, when we're multiplying this whole thing times 4, what does that mean? Well, that means we're just going to add this to itself 4 times. So let me do that with the copy and paste. Copy and paste. Let me copy, and then let me paste. There you go. That's 2. That's 1, 2, 3. And then we have 4. And we're going to add them all together. So this is literally what 4 times, right? We have it. Let me go back to the drawing tool. We have it 1, 2, 3, 4 times this expression, which is 8 plus 3. Now, what is this thing over here? What is this thing over here? What is this thing over here? If you were to count all of this stuff, you would get 44. But what is this thing over here? Well, that's 8 added to itself 4 times. You could imagine you're adding all of these. So what's 8 added to itself 4 times? That is 4 times 8. So this is 4 times 8.
4
and
times.
what is this over here in the orange?
That like
we have 1, 2, 3, 4 times. Well, each time we have 3.
40.
So it's 4 times this right here.
Oh yeah, if you have like 8 and then added to itself like 4 more times.
This right here.
And it's like 8 plus 8 times 4.
Is 4 times 3. So you see why the distributive property works. If you do 4 times 8 plus 3, you have to multiply when you, I guess you could imagine, duplicate the thing 4 times. Both the 8 and the 3 is getting duplicated 4 times, or it's being added to itself 4 times, and that's why we distribute the 4.
One times x minus 1 square. 6 plus x minus 5. Yo. Distributive multiplication. There's no multiplication happening in this example B. So I guess you kind of distributed the signs, so you get like then -5. Same thing if you just remove this. Oh, stupid parenthesis shit. So he kind of remove that so we can. Okay, cool. We usually they're not like terms. Make sure you apply the outside. Make sure you apply the outside number to all of the terms inside. Okay. Okay. 10 times 2 plus 3. The greatest common factor of 20 and 30. What? This is insane. What? Yo, it's kind of hard. Okay.
Rewrite the expression 5 times 9 minus 4, that's in parentheses, using the distributive law of multiplication over subtraction. Then simplify. So if we, let me just rewrite it. So this is going to be 5 times 9 minus 4.
45 minus 20, you get 25.
9
but if I do it the traditional way, we get
just like that. Now, if we want to use the distributive property, you don't have to. You could just evaluate 9 minus 4 and then multiply that times 5. But if you want to use the distributive property, you distribute the 5. You multiply the 5 times the 9 and the 4. So you end up with 5 times 9, 5 times 9 minus 5 times 4. Minus 5 times 4. Notice we distributed the 5. We multiplied it times both the 9 and the 4. And in the first distributive property video, we gave you an idea of why you have to distribute the 5, why it makes sense, why you don't just multiply it by the 9. And we're going to verify that it gives us the same answer as if we just evaluated the 9 minus 4 first. But anyway, what are these things? So 5 times 9, that is 45. So we have 45 minus, what's 5 times 4? Well, that's 20. 45 minus 20, and that is equal to, well, that's equal to 25. So this is using the distributive property right here. If we didn't want to use the distributive property, if we just wanted to evaluate within the parentheses first, we would have gotten, let's go in this direction, 5 times, what's 9 minus 4? 9 minus 4. 9 minus 4 is 5. We'll do that in a different color. 5 times 9 minus 4. So it's 5 times 5. 5 times 5 is just 25. So we get the same answer either way. This is using the distributive law of multiplication over subtraction, usually just referred to as the distributive property. This is evaluating the inside of the parenthesis first and then multiplying by 5.
We're asked to rewrite the expression 7 times, open parentheses, 5 plus 11, close parentheses, as the sum of 35 and another whole number. So really what they're asking us to do is just apply the distributive property. We have 7 times the quantity 5 plus 11. Now this is easy to calculate. You can just say 5 plus 11 is 16, and then 16 times 7 is what? That's 70 plus 42, which would be 112. But that's not what they're asking us to do. They're not saying just calculate this. They're saying express this as a sum of 35 and another whole number. So let's apply the distributive property, and let's see if we can get a sum of 35 and another whole number. So 7 times 5 plus 11, that's the same thing as 7 times 5 plus 7 times 11. And you can see with this expression editor right over here, it tells you, it puts it kind of the nice math formatting for what it looks like for the computer. So if we're distributing the 7 over the 5 and the 11, it's 7 times 5 plus 7 times 11. Well, 7 times 5 is 35. and 7 times 11 is 77. Now, have we done what they're asking us? They said rewrite this expression as the sum of 35 and another whole number. Well, we've done that. We've written it as the sum of 35 and another whole number, and we were able to do it using the distributive property. So let's check to make sure that we got the right answer. Yes, we did. Let's do one more of these. Rewrite the expression 12 plus 75 in the following form. A times 4 plus C, where A and C represent whole numbers. Now, this might look complex, but they're really asking us to factor out an A, factoring out an A out of this expression right over here, seeing how much we can factor out so that one of these two numbers becomes a 12, or becomes a 4. So let's think about how to do that. If we look at these two numbers, the greatest common divisor of 12 and 75 looks like it is 3. 3 is definitely divisible into, or both of them are divisible by 3. So you can write 12. 12 is the same thing as 3 times 4. And 75 is the same thing as 3 times 25. Now, what we could do is we can essentially factor out the 3. So this is, or you could say we're undistributing the 3. So that's the same thing. 3 times 4 plus 3 times 25. That's the same thing as 3. That's the same thing as 3 times 4 plus 25. 3 times 4 plus 25. And it looks like we've actually put it in the form that they want us to put it in, where 3 is A and 4 is right there, it's 4, and then C is 25. So we've put it in the right form. Let's check our answer. We got it right.
Oh, that's insane. Very cool. Okay.
What we're going to do in this video is dig a little bit deeper into our understanding of multiplication. And just as an example, we're going to use 4 times 7. And some of you might know what 4 times 7 is, but even in this case, I think you might get something from this video, because we're going to think about how you can break down a multiplication question into simpler parts. And that's going to be useful well beyond 4 times 7. It's going to be useful in your future when you're tackling more and more complicated things. Now, there's a couple of ways that we can visualize 4 times 7. My favorite way is to visualize it with angry cats. So let's bring on the angry cats. Yep, they're still angry. And we can see that this is a representation of 4 times 7. We have 4 rows right over here. 4 rows. And each of those rows have 7 cats. And so you can see that right over here. Each of those rows have 7 cats. Some people would call this a 4 by 7 grid or 4 by 7 array, however you'd want to view it. But if someone were to ask you what's the total number of cats, it would be 4 rows times 7 columns. 4 times 7. Now, another way to represent 4 times 7 is also with a tape diagram. You might see something like this, where here we're visualizing it as 7 4s. Or you could view it as 4 plus 4 plus 4 plus 4 plus 4 plus 4 plus 4. Now that's all well and good, and you can add that up if you like. But what I promised you is that we would figure out ways to break down things that might simplify things in the future. Well, what if you didn't know what 4 times 7 is, but you knew what 4 times 5 is, and you knew what 4 times 2 is? Well, what's interesting is that 7 is 5 plus 2. So what if we tried to first figure out this many cats? So 4 rows and 5 columns,
it's the same
right over there.
Earlier.
And then
No,
we tried to
cats.
figure out this many cats, 4 rows and 2 columns. And you can see that it's the exact same number of cats. So one way to think about it is 4 times 7 is the exact same thing as 4 times, and I'm going to use parentheses, and that just means to do that part first,
5 plus
is
2.
equal to 4 times. Instead of 7, I could write that as 5 plus 2, because that's what 7 is. So all this is saying is 4 times 7 is the same thing as 4 times 5 plus 2, where you do the 5 plus 2 first because we have those parentheses around it, and 5 plus 2 is indeed equal to 7. And we can see that that is equivalent to the total number of cats that we have here, which we could view as what we just circled off in this orangish pink color, which would be 4 rows of 5. So that would be equal to 4 times 5. 4 times 5. And then to that, we can add this second group of cat heads or angry cat heads, and that is 4 rows of 2. So that's 4 times 2. And we could put parentheses if we want, just to make it a little bit more readable. Now, why did I do that? Well, some folks might find 4 times 5 a little bit more straightforward. I could skip count by 5. I can go 5.
I'm gonna grab a drink.
Five, 10, 15, 20. Also, 4 times 2 might be a little bit more straightforward. And so it could be easier to say, hey, this is just going to be 4 times 5, which is 20, plus 4 times 2, which is equal to 8. And so that is just going to be equal to 28. And you could have thought about it the same way down here with what is sometimes called a tape diagram. We could say, all right, if I have 5 4s, that's this amount right over here. That is the 4 times the 5. And then I could add that to the 2 4s, the 4 times the 2 right over here. And that's another way to get to 4 times 7. So the big picture here is, even if you're not dealing with 4 times 7, even if you're not dealing with angry cats, and in most of our lives we actually try to avoid angry cats, there might be a way to break down the numbers that you're multiplying into ones that you might be more familiar with. I'll give you one more example. Let's say someone were to ask you, well, what is 6 times 9?
Oh, it's 54.
Pause this video and see if you can break this down in some useful way.
I can do it.
Well, maybe you know what 6 times 10 is. And you also know what 6 times 1 is. So you could rewrite 9 as 10 minus 1. Well, then this would mean that 6 times 9 is the same thing as 6 times 10 minus 1. Based on exactly what we just did up here, that says that this whole thing is going to be the same thing as 6 times 10,
Oh, it's pretty cool.
6 times 10 minus 6 times 1. One way to think about it is I just distributed the 6. That's the distributive property right over there. And then 6 times 10 is equal to 60. And then 6 times 1 is equal to 6. And it might be easier for me to say, hey, 16 minus 6 in my head, that's equal to 54. So I know what some of you are thinking. 6 times 9 seems so clean, and now I've involved all of this other symbols, and I've written down more numbers. But at the end of the day, I'm trying to give you skills for breaking down problems, and including ways that you might want to do it in your head. If you're like, hey, I'm kind of foggy on what 6 times 9 is, but 6 times 10, hey, I know that's 60, and 6 times 1, of course, that's 6. Well, what if I view this as 6 times 10 minus 1? And then I could tackle it and get 54. And once again, you might know 6 times 9. You might know 4 times 7. But in the future, it might be useful for bigger and bigger numbers to think about, how can I break this down?
So this is the sum of two numbers. The product doesn't change. 5 could be written as 2 plus 0 problems. This is solved to simpler multiplying. We can change 4 times 7 to 4 times 10 plus 2. Then 4. The array of dot subset is 10. The array of 4 times 7 again. 4 times 8. Practice. The dots below represent 12 times 2. They are broken up to reduce 6. 6 times 2, right? Find breaking 7 into expressions. Oh, okay. What is this? This is hard, yeah. It's gonna be like 5. 40. And 6. Broken up. 9 to 4 times 4. Yeah, like 16 or 6. Before this, after the distributive property, match equivalent expressions. Let's see, we have 4, we have 5 and 2, right? And then 5 and 4 are 4. Okay. Cool. next video. Yo, we're gonna do the almost 2 hours. I think I can finish this as long as I don't make any mistake. Please. I value 7 times 4 is equals to 5 fours plus 2 fours. 2 fours, 8. 9 times 8 is equal to 10 times 8 minus 1 times 8 minus 8, 7. 6 times 6, 5 sixes and 1. No, 2 sixes. Then 12, and then like 5 sixes, 30. And 42. No, it's 35. It's 49. What's this 30? Dude. I made a typo. I hate typo mistakes. 10 fours is 90. Wait, 10 fours? No, it's 40. And then minus 4 is 36. 4 times 6 and then 4 is 48. 9 times 10, 10 ones, 10 nines minus 1 9. 81. 7 times 5 is 5 times 8 plus 2 times 8 and 16.6. Please correct. Boom. Visualize distributive property. Use a tape diagram to break 8 times into 2 groups. Okay. 5 fours plus 3 fours. Use the image of 9 times 8 into 2 expressions. Okay, this 9, it's gonna be 5 times 8, and it's gonna be like 32. Was 70 correct? Yeah, it's correct. 5 fours and 3 fours. Hey, this is the same thing from earlier. 52. Wait, what? Times 4? No. 5 fours is 20, dude. 32. 3 fours. Yeah. This erasing is to bring the two things. Okay. It's gonna be 3 fours plus 3 fours is this visual thing. It's 3 fours plus 3 fours. Factor with distributive property, no variables. Plus into factor the greatest common factor. Oh shit, it's gonna be 5, right? Oh my god, this is insane. 11 plus 7. Would this be correct? Oh my god. Cool. Oh shit, seems like 5 as well. What are the greatest common factor? I don't know. 10 and 5 as well, I think. 5 times 10, 15 plus 4. Yo, I don't know. It seems like all 5s. Addison's always by 3, 5 is 7. We can do it by 6, 1 plus 6. Oh no. Two, right? 4. We have 4. We have 8 and 12. No, not 12. It's 11. Not 4. Because you can get in 4. 6 is 3. 4. I think I just do. Let's try 12 and 14. Seriously? I leveled down. Insane. So good it's not like fucking quiz or something. If this is by 6 or 16 now. Let's try 4. Yeah, 4. I have 3 and 20. That's correct. 18, 12. Okay. Oh no, it's plus. Multiply. What is multiply? Plus. Wait, what? What is this? Okay, there we go. 4, 10. I guess 2. We have 2 times 2 plus 5. No. Yeah. Let's say 4. 3 plus 5. 56 would be by 8, right? 8. 7 is 4. 8. 36. 4. Okay. Could be by 4 as well. 4, 11 plus 12. And this could be by not 7, not oh shit, by 6. 5 plus 7. Okay. So this is by 4, I think. Yeah. By 4 plus this is 9. I guess it's 9. No, okay, we're almost close.
So let's talk a little bit about rational numbers. Rational numbers. And the simple way to think about it is any number that can be represented as the ratio of two integers is a rational number. So, for example, any integer is a rational number. 1 can be represented of 2 that can be represented as the ratio of two integers is a rational number. So, for example, any integer is a rational number. 1 can be represented as 1 over 1, or as -2 over -2, or as 10,000 over 10,000. In all of these cases, these are all different representations of the number 1, ratio of two integers. And I actually obviously can have an infinite number of representations of 1 in this way, the same number over the same number. The number -7 could be represented as -7 over 1, or 7 over -1, or -14 over +2, and I could go on and on and on and on. So -7 is definitely a rational number. It can be represented as the ratio of two integers. But what about things that are not integers? For example, let us imagine, let's imagine 3.75. How can we represent that as the ratio of two integers? Well, 3.75, you could rewrite that as 375 over 100, which is the same thing as 750 over 200. Or you could say, hey, 3.75 is the same thing as 3 3/4, So let me write here, 3 3/4, which is the same thing as, that's 15 over 4. 4 times 3 is 12, plus 3 is 15. So you could write this. This is the same thing as 15 over 4. Or we could write this as negative 30 over negative 8. I just multiplied the numerator and the denominator here by negative 2. But just to be clear, this is clearly rational. I'm giving you multiple examples of how this can be represented as the ratio of two integers. Now what about repeating decimals? Well, let's take maybe the most famous of the repeating decimals. Let's say you have 0.333, just keeps going on and on forever, which we can denote by putting that little bar on top of the 3. This is 0.3 repeating. And we've seen, and later we'll show that how you can convert any repeating decimal into a rational as the ratio of two integers. This is clearly 1 over 3, or maybe you've seen things like 0.6 repeating, which is 2 over 3. And there's many, many, many other examples of this. And we'll see any repeating decimal, not just one digit repeating, as many, even if it has a million digits repeating, as long as the pattern starts to repeat itself over and over and over again, you can always represent that as the ratio of two integers. So I know what you're probably thinking. Hey Sal, you've just included a lot. You've included all of the integers. You've included all of non-repeating decimals, or you've included all of finite non-repeating decimals, and you've also included repeating decimals. What is left? Are there any numbers that are not rational? And you're probably guessing that there are. Otherwise, people wouldn't have taken the trouble of trying to label these as rational. And it turns out, as you can imagine, that actually some of the most famous numbers in all of mathematics are not rational. And we call these numbers irrational. Irrational numbers. And I've listed just a few of the most noteworthy examples. Pi, the ratio of the circumference to the diameter of a circle, is an irrational number. It never terminates. It goes on and forever, and it never repeats. E, same thing, never terminates, never repeats. It comes out of continuously compounding interest. It comes out of complex analysis. E shows up all over the place. Square root of 2, irrational number. Phi, the golden ratio, irrational number. So these things that really just pop out of nature, many of these numbers are irrational. Now you might say, okay, are these irrational? These are just kind of these special kind of numbers. But maybe most numbers are rational, and Sal's just picked out some special cases here. But the important thing to realize is they do seem exotic, and they are exotic in certain ways, but they aren't uncommon. It actually turns out that there is always an irrational number between any two rational numbers. And in that, well, we could go on and on. There's actually an infinite number. But there's at least one. So that gives you an idea that you can't really say that there are fewer irrational numbers than rational numbers. And in a future video, we'll prove that you give me two rational numbers, rational 1, rational 2, there's going to be at least one irrational number between those, which is a kind of a neat result because irrational numbers seem to be kind of exotic. Another way to think about it, I took square root of 2, but you take the square root of any non-perfect and erratic in certain rational numbers. So these things that really just pop out of nature, many of these numbers are irrational. Now you might say, okay, are these irrational? These are just kind of these special kind of numbers. But maybe most numbers are rational, and Sal's just picked out some special cases here. But the important thing to realize is they do seem exotic, and they are exotic in certain ways, but they aren't uncommon. It actually turns out that there is always an irrational number between any two rational numbers. And in that, well, we could go on and on. There's actually an infinite number. But there's at least one. So that gives you an idea that you can't really say that there are fewer irrational numbers than rational numbers. And in a future video, we'll prove that you give me two rational numbers, rational 1, rational 2, there's going to be at least one irrational number between those, which is a kind of a neat result because irrational numbers seem to be kind of exotic. Another way to think about it, I took square root of 2, but you take the square root of any non-perfect square, you're going to end up with an irrational number. You take the sum of an irrational and a rational number, and we'll see this later on. We'll prove it to ourselves. The sum of an irrational and a rational is going to be irrational. The product of an irrational and a rational is going to be irrational. So there's a lot of irrational numbers out there. Which of the following real numbers are irrational? Well, irrational just means it's not rational. It means that you cannot express it as the ratio of two integers. So let's see what we have here. So we have the square root of 8 over 2. So square root of 8, if you take the square root of a number that is not a perfect square, it is going to be irrational. And then if you just take that irrational number and you multiply it and you divide it by any other numbers, you're still going to get an irrational number. So square root of 8 is irrational. You divide that by 2, it is still irrational. So this is not rational, or another way of saying it, it is irrational. Now you have pi, 3.14159. It just keeps going on and on and on forever without ever repeating. So this is irrational, probably the most famous of all of the irrational numbers. 5.0. Well, I can represent 5.0 as 5 over 1. So 5.0 is rational. It is not irrational. 0.325. Well, this is the same thing as 325 over 1,000, so I can clearly represent it as a ratio of integers. So this is rational, just as I could represent 5.0 as 5 over 1. Both of these are rational. They are not irrational. Here I have 7.777777, and it just keeps going on and on and on forever. And the way we denote that, you could just say these dots that say that the 7s keep going, or you could say 7.7, and this line shows that the 7 part, the second 7, just keeps repeating on forever. Now, if you have a repeating decimal, in other videos we'll actually convert them into fractions. But a repeating decimal can be represented as a ratio of two integers, just as 1/3 is equal to 0.333, on and on and on, or I could say like this. I could say 3 repeating. We can also do the same thing for that. I won't do it here, but this is rational, so it's not irrational. 8 1/2. Well, that's the same thing. 8 1/2 is the same thing as 17 halves, so it's clearly rational. So the only two irrational numbers are the first two right over here.
Cool, okay. Numbers are numbers that do not need to be represented with a fraction. Also, numbers cannot be negative. Now, there's some numbers are the counting numbers and 0. Wow, okay. Integers are whole numbers and their opposites. Therefore, integers can be negative. Oh, cool, okay. Can be expressed as a fraction of two integers. Rational. Okay. Rational numbers can be expressed as a fraction of two integers. Examples of irrational numbers. How are the types of numbers numberly? The following diagram shows that all numbers are integers and all integers are rational numbers. Numbers that are not rational are called irrational. Okay. It's irrational. Or whole number. Oh, it's also an integer and irrational. It's all no whole number, it's an irrational. Oh, this one's an integer. And rational. Okay, I'm not gonna take the quiz yet. I'm gonna do these practices. Okay, cool. This one, it's irrational. Oh, it's rational. 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 It's a perfect square. It's rational, right? Yo, what up? Cool. Let's start the quiz. Yo, am I supposed to answer this? Okay. It's gonna be 6 times 4 is 438. Lead multiplies 9 and find them. Who's correct? I think Sarah is correct. It's not 9 times 9. I see the number, it's rational. Okay. 2 times 3 or 352, 352, 352. Apply the distributive property factor at the greatest common factor. Oh, the greatest common factor is 2, guys. It's 7. 7 and 5 plus 2, right? Okay. Yeah. Which is going to represent the following picture? 2 expressions. 4 and 2. It's 2 times 8 or 8 times 2. Aaron tried to evaluate an expression step by step. Find Aaron's mistake. Aaron. Step 1. Then, why did this become 16? I mean, yeah. Match its expression to its exponential form. Okay, so 2 times 4 times 6. Yo, what's this? 4, 2, 4, 8, 16. Okay. Use the tape diagram to break 9 times 6 into 2 groups. 1, 2, 3, 4, 5. 5 sixes and 4 sixes. It's gonna be 5 eighths and 3 eighths, 24, 64. Complete the equation. Okay. 7 times 2 times 5, 70, right? Then 70. Yeah. Wow, I'm much more confident. It's probably because it isn't the unit test. It's the unit test. So an overview of what we did: place values, terminal numbers, grouping shit. Okay, cool. Just do all the shit. Okay, starting the test. 18 questions, 15 to 19 minutes. What is the first step to evaluate? Then select 7. Apply the distributive property factor to the greatest common factor. 3 and 3 plus 5. It's irrational. Okay, 1, 2, 3, 5, 4. 4 fours. 16. 36. Yep, that's right. In standard form. Oh shit. 600,000 plus 40,000 plus 300 plus 80. Okay, cool. Which of the following place value tables shows 7,082? Okay, 7,082. This one's correct. 8 tens and 2 ones. No. Choose one answer. Oh, this hundreds. Okay, with thousands. Sam says the image represents 3 times 9 or 3 groups of 9. Then 9 groups of 3, okay. Fill in the blanks to solve 4 times 600. Yo, this is hard. This is correct. Yeah, I guess this is correct. 900 is 90 tenths. Find the products. Okay, it's from 30, right? So 15, 30, yeah, cool. Which two expressions are equivalent to 6 times 2 times 5? Not 12 times 5. 12 times 5 or 6 times 2 times 5. Okay. 700 times 10 equals 70 hundreds or 7,000s. That's insane, man. Rounded to the nearest hundred. Right? 2,800. Nearest hundred. Round down. Cool. 3 times. What is this? 3? Yo, yeah. 3 times 6. That's just 8 as well, so. It's gonna be 3 times 9. 54. 4, right? 6. Yo. This is 9 times 6. 4. Yeah, I agree about that because 18 times 3 is like 3, 24, 54. What is this? 9. And then we have like 7. So we have like, holy shit, what is this? That's 72, right? 6 and 12, 72. Yeah, cool. Bow has 56 cards. What are 2 ways bow? How important? Okay, cool. What are 2 ways bow can stack their cards? 2 ways we can do. It's not 6 times 9. It's 8 stacks. So this is 54. Evaluate the expression, the following expression. Yo, what is this? Last question's insane. Okay. Am I just supposed to answer this? Okay. Using the PEMDAS shit? Okay. 6 times 6, you have 36. Let's write it. 6 times 6, 36. Times 6, you have 6, 3, 18, 21 times 6, 36, 3, 6, 9, 12. Plus 6 times 2 is 12, so plus 12. Yo, okay, so we have like 1308. Oh my god, this is insane. Okay, 8, 10, 3. Okay, let's try to answer this again. I'm gonna answer this 3 times. Okay, 6 times 6. No, not really. Just gonna do 36. Then multiply that by another 6. 36. 3. 18. 21. So 6, 36 again. 36, 3, 6, 9. I got 12. Then we have 6 times 2 is 12, so we add that 2 shit together. We have 8, 10, 3, 1308. Yeah, man, let's go. Mastered. Cool. Yes, cool. So yeah, I guess I finished this section. Feels good, man. 100%. So 43, how much we earn? Or 43%, became, wow, 48. We gained 5%. That's cool. Okay. Notifications 10 minutes, 41 minutes. Okay. World of Math are 18, still 18%. Yeah, it's sad. Didn't move, what the hell? Okay. Or I haven't just refreshed it, or it's just really 18%. Okay, it's really 18%. 48. Okay. So for the next part, we're gonna be in factors and multiples. Okay. Thanks. Bye.